Look up at the night sky. What you see is just a tiny fraction of the vast cosmos that surrounds us. Every star, every planet, every galaxy we can see belongs to a sphere of space we call the observable universe. This is the region of the universe that we can observe, thanks to the light and other signals that have had time to reach us since the beginning of the cosmic expansion. It's a vast expanse, stretching for billions of light years in every direction. Imagine the sheer scale of it, billions of galaxies, each containing billions of stars, all spread out over an incomprehensible distance. But it's not all there is. The observable universe is just a small part of a much larger, possibly infinite cosmos. Beyond the limits of what we can see, there may be countless more galaxies, stars, and planets. It's just the part we can see. Our telescopes and instruments, no matter how powerful, are limited by the speed of light and the age of the universe. Imagine a tiny ant on a giant beach ball. The ant can only see a small area around itself, unaware of the vast surface that lies beyond its immediate view. The ant can only see a small area around itself. That's our situation. We are like that ant, confined to our little patch of the cosmos, unable to see beyond the horizon of our observable universe. We're like the ant, confined to our little patch of the cosmos. Our view is limited, but that doesn't mean there's nothing beyond it. In fact, the universe likely extends far beyond what we can observe, filled with wonders we can only imagine. The observable universe is our cosmic bubble, a tiny glimpse into the grand tapestry of existence. This bubble is defined by the distance that light has traveled since the beginning of the universe, giving us a snapshot of the cosmos as it was in the past. The size of our observable universe is determined by two things: the speed of light and the age of the universe. Light, the fastest thing in the universe, still takes time to travel across the vast distances of space. Light travels incredibly fast, but it still takes time to reach us. Even the light from our nearest star, Proxima Centauri, takes over 4 years to get here. The farther away an object is, the longer it takes for its light to arrive. This means that when we look at distant galaxies, we are actually seeing them as they were millions or even billions of years ago. Because the universe has a finite age, around 13.8 billion years, we can only see objects whose light has had time to reach us since the Big Bang. This creates a cosmic horizon, beyond which we cannot see. This creates a limit, a boundary beyond which we cannot see. But this boundary is not the edge of the universe, it's simply the edge of what we can observe. The true size and nature of the universe remain one of the greatest mysteries of science, inviting us to explore and discover more about the cosmos we call home. There's a point in the distance where the light from the most distant objects hasn't had time to reach us yet. This point marks the boundary of what we can observe in the universe, a limit defined by the speed of light and the age of the universe itself. Beyond this boundary, the universe continues to exist, but its light hasn't reached us, making it invisible to our telescopes and instruments. This is the edge of our observable universe, often called the cosmic horizon. It's a fascinating concept because it represents the furthest we can see, not because of any physical barrier, but due to the finite speed of light and the vast distances involved. The cosmic horizon is a dynamic boundary, constantly changing as the universe ages and expands. It's not a physical barrier, but rather a limit imposed by the nature of light and the expansion of space. As the universe expands, space itself stretches, causing the light from distant galaxies to take longer to reach us. This stretching of space also means that the light we see from these galaxies is redshifted, shifting towards the red end of the spectrum and becoming fainter. Think of it like a ship sailing on the ocean. The horizon is the furthest point the sailors can see, but it's not a fixed point. As the ship moves forward, the horizon moves with it, revealing more of the ocean. This analogy helps us understand the concept of the cosmic horizon in a more tangible way. The horizon marks the farthest point the sailors can see. Similarly, the cosmic horizon marks the furthest point we can observe in the universe. Just as the sailor's view expands as they move forward, our view of the universe expands as time progresses, and more light from distant objects reaches us. As the ship moves forward, the horizon expands, revealing more of the ocean. In the same way, as time passes and the universe continues to expand, our cosmic horizon expands, bringing more of the universe into view. However, this expansion is not without its complexities and challenges. Similarly, as time passes, our cosmic horizon expands, bringing more of the universe into view. However, there's a catch. The universe isn't static, it's expanding. This expansion affects how we perceive distant objects and how the cosmic horizon itself evolves over time. The universe isn't static, it's expanding. This expansion means that galaxies are moving away from us and the space between them is stretching. The rate of this expansion is not constant, it's actually accelerating, driven by a mysterious force known as dark energy. And it's not just expanding, the rate of expansion is accelerating. This acceleration means that galaxies are moving away from us at increasing speeds. The farther away a galaxy is, the faster it appears to be receding from us. This phenomenon has profound implications for our understanding of the universe's future. This means that galaxies are moving away from us, and the farther away they are, the faster they're receding. At a certain distance, known as the Hubble radius, galaxies are receding from us at the speed of light. Beyond this radius, galaxies move away faster than light, making them effectively unreachable and unobservable. At a certain distance, galaxies are moving away from us faster than the speed of light. This doesn't mean they're breaking the cosmic speed limit. Instead, it's a result of the expansion of space itself. The galaxies aren't moving through space faster than light, rather the space between us and them is expanding. This doesn't mean they're breaking the cosmic speed limit. The speed of light remains the ultimate speed limit for any object moving through space. However, the expansion of space itself can cause galaxies to recede from us at speeds greater than light, without violating any physical laws. Instead, it's space itself that's expanding, carrying the galaxies along with it. This expansion stretches the light from these galaxies, causing it to redshift. The greater the distance, the more pronounced the redshift, making these galaxies appear fainter and more challenging to detect. The light from these distant galaxies is stretched and redshifted, becoming fainter and harder to detect. This redshift is a key piece of evidence for the expanding universe, and helps astronomers measure the rate of expansion. As we continue to explore the cosmos, the cosmic horizon will keep expanding, revealing more of the universe's secrets and deepening our understanding of the vast, ever-changing cosmos. The idea of a universe beyond our own, a multiverse, has captivated scientists and philosophers for centuries. If our universe is finite, what lies beyond its edge? Could there be other universes out there, perhaps governed by different laws of physics, containing different forms of matter and energy? The multiverse hypothesis, while still speculative, offers a tantalizing possibility that our universe is just one of many, a single bubble in a vast cosmic foam. There are different models of the multiverse, each with its own set of rules and implications. One model suggests that our universe is embedded in a higher dimensional space, like a bubble in a pot of boiling water. In this scenario, other universes could exist as separate bubbles, potentially colliding or interacting with our own. Another model, arising from the theory of cosmic inflation, proposes that our universe is just one of countless pocket universes that emerged from a period of rapid expansion in the early universe. Each pocket universe could have different physical constants and properties, leading to an incredible diversity of cosmic landscapes. While we can't directly observe what lies beyond the cosmic horizon, modern physics provides us with tantalizing clues. These clues come from a variety of sources, including theoretical models, astronomical observations, and complex simulations. By piecing together these bits of information, scientists are able to construct a more comprehensive picture of the universe and its origins. The theory of cosmic inflation, which describes a period of exponential expansion in the first fraction of a second after the Big Bang, has profound implications for our understanding of the universe's structure. This rapid expansion smoothed out any irregularities and set the stage for the formation of galaxies, stars, and planets. It also helps explain why the universe appears so uniform on large scales, despite the chaotic conditions that existed in its earliest moments. Inflation suggests that our observable universe is just a tiny patch of a much larger entity, a vast cosmic landscape that was smoothed out and stretched during this early period of rapid growth. This means that what we can see with our telescopes is only a small fraction of the entire cosmos. Beyond our observable universe, there could be regions with different physical properties governed by different laws of physics. This process could have created other regions of space that underwent similar inflationary periods, leading to the formation of other universes. These other universes might have different constants and particles, resulting in a multiverse with a diverse array of possible realities. The idea of a multiverse challenges our understanding of existence and raises profound questions about the nature of reality itself. Furthermore, the study of the cosmic microwave background radiation, the faint afterglow of the Big Bang, provides us with a snapshot of the universe's infancy. This radiation, which has been traveling through space for over 13 billion years, carries with it information about the conditions that prevailed in the early universe. By analyzing this ancient light, scientists can learn about the processes that shaped the cosmos. Analysis of this radiation reveals subtle temperature fluctuations that provide evidence for inflation and hint at the possibility of a multiverse. These tiny variations in temperature are like fingerprints, offering clues about the events that occurred in the first moments after the Big Bang. They suggest that the universe underwent a rapid expansion, which smoothed out any irregularities and created the large-scale structure we observe today. These fluctuations, like ripples on a pond, suggest that our universe was once connected to something larger, a primordial soup of energy and matter from which our universe and potentially others emerged. This primordial state was a seething cauldron of particles and forces, constantly interacting and evolving. As the universe expanded and cooled, these interactions gave rise to the structures we see today, from galaxies and stars to planets and life itself. The study of these early conditions helps us understand not only where we come from, but also the fundamental nature of reality.